Hello. We started yesterday by looking at the basic mathematical foundations of what we're going to talk about in this course, namely manifolds. So they're the things that we want to talk about. But in math, we like to set up our language about what we want to talk about by talking not only of the things we want to talk about, but the maps between the things. What are we going to allow? And so one talks of a category in mathematics, which I'm not going to define for you in this course, but when you hear the words category said by a mathematician, what they're saying to you is this is the language that we want to use in our discourse about this subject, and the bare minimum is captured by this notion of a category, the bare minimum language. And a category, what does it consist of? It consists of a bunch of things and maps between things. And so once you've said, okay, these are the things that I care about, then you're not quite there. If you want to have a meaningful discussion in maths, you need to talk about what maps are we going to allow between the things. How can the things change? How can we compare the things? And so a category is a way of quantifying or making concrete this idea that to talk about something in maths, we need to say what are the things and the maps between the things. So of course the mathematicians don't use the words things, they use a different name for the things. They're called objects in a category. What are your objects? And the maps between things are called morphisms. And so far in this course, in the first lecture, I've been telling you what are the things, the objects, and the objects for us are manifolds or differentiable manifolds. But I haven't told you what are the maps between them. How are we going to map from one thing to another, one object to another, one manifold to another? We need to work that out. We need to say what we're going to allow and what we're not going to allow. And that's the purpose for today. And once we've set our language, once we've set the landscape of objects that we're going to talk about and the maps between them, then we can start to derive consequences and learn about these things. So that's why today's topic is that of differentiable maps, or differentiable maps. These are the morphisms that we're going to allow between our objects, the maps. We're not going to allow arbitrarily crazy maps, we're going to allow differentiable maps. And the idea is to just take what we know from affine space. As I said yesterday, a manifold is just like a way of generalizing normal flat space to a slightly more general context. So we take what we know there and transfer those ideas as best we can to this more general context of manifolds. So firstly, well, a differentiable map, as the name suggests, must be a map. It's some kind of thing that maps between two of our allowed objects. Remember, our objects now are manifolds. So let it be a map. So a map is something that makes sense when you have a set and a set. So manifolds are at least sets because they're locally Euclidean spaces, which are topological spaces, which are have sets underlying their definition. So F is a map between two sets. So we can talk about the word map. And we're further going to say that M is an m-dimensional manifold and N is an n-dimensional manifold. Great. So that's a map. And we're going to give some conditions under which this map is differentiable or not. So if you have some point in the manifold M, because it's a map, there's going to be a point in the manifold N. That's what it means to have a map. Okay, a point in M gets mapped to N. Now, if we left it at that, there's not much more we can say. We're going to have to exploit the fact that we know more about these things called manifolds, namely that they look locally like flat space. And that'll allow us to say things about differentiability. Like we want to take the derivative of something. And as written, we don't really have that extra data to allow us to take a derivative. We don't even know what points are nearby at this point. We have to exploit the information we know about manifolds, that they're locally Euclidean, to talk about derivatives. You compare two things. And whenever you want to compare points on a manifold, you have to take a chart, right? You have to take some set around this point P, map it to Euclidean space with our coordinate system, and then you can do everything there as you would in flat space. So we've got to take some charts now around our points. P is an element of U, and f of P is an element of V. So we take the correct charts. And in order to start talking about derivatives, we need to get it to a state where we can compare things at nearby points. We can only do that in Euclidean space so far. And the way we do that is we get a presentation of our function on Euclidean space via these coordinate systems phi and psi. I'll draw a picture in a second. And this is this coordinate presentation here, this function that goes from the space we know and love to another space we know and love. That's what we work with when we define the words differentiable. So the coordinate presentation of f is this thing here, and we know that such a thing exists because it comes from the definition of a manifold as a locally Euclidean space. Well, n is a second countable, blah, 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 blah. And then that's what we're going to work with to define differentiability. So before I quite get to that definition, I'll draw a picture just to keep track of where things are going to and coming from. here's the picture that's relevant to this definition. So we have a manifold M, we have a manifold N. Okay, that's what we started with, and a map between them. So here's a point P, here's a map between them, F, here's F of P, and then we've taken, in order to be able to talk about derivatives and differentiability and so on, we have to relate it to Euclidean space in some way where we do know how to talk about derivatives. So we take a chart, U, which is a neighborhood around this point P, and a corresponding map phi to Euclidean space, and our point is like somewhere here. And we do the same around here. This is V. Take it to Euclidean space. Here's f of p. Oops, that was wrong. That's psi of f of p. And this is phi of p here. And then a map F induces a map between our nice affine spaces here, our Euclidean spaces. And the map it induces is, well, you take this point here, you find its pre-image under phi, you apply F, and then you apply psi. So there is a map between this point and this point here, and that map is precisely, well, I'll do it backwards. Like, first find the pre-image of this point. So now we've got a point in the manifold, do our function f, and then find out where it lands in that chart there. So that sequence of 3 operations is exactly this function here. I hope at this stage already, like this insistence on drawing a picture every time we have a definition will start to seem worthwhile. Because if we just left it at symbols, like I personally find it very difficult to follow 2 or 3 composition steps with functions. But maybe you can deal with this. But as we get on in the course, we're going to talk about dual spaces and differential forms, and then we'll have maps on maps going between spaces of maps on maps and so on. And that's when these pictures become totally essential. As long as you know where you're going to, where you've come from, and how you got there, then you're pretty much right in differential geometry. Everything gets set by these things. All right, so this is an ordinary, this is a map from Rm to Rn. So actually that's something that you've encountered before in multivariable calculus. So let's just deal with it using the tools of multivariable calculus. So we're going to, for the point phi of p, we're going to give it some coordinates, or it has some coordinates in Rm, this point phi of p. We'll give those coordinates a name. X mu for the coordinates of phi of p. Just a list of m real numbers. And then there's another point in a Euclidean space we have to worry about, and that's f of p, or psi of f of p. All right, that's what we're going to call those coordinates, y of nu. Mu runs from 1 to m, nu runs from 1 to n. But you'll be used to this after a while. I won't write these limits after today, probably. So we can write our coordinate presentation in coordinates just like that. Hopefully this makes you think of ordinary vector-valued functions, because that's exactly what it is. And because we tend to suppress indices in differential geometry, I'm going to almost certainly end up writing it like this. So this looks like a single variable function. It's not. You have to look at the context of the definition to work out what this means. So this really stands for that, and that stands for the coordinate presentation of this map between manifolds. Okay, well, we have an ordinary vector-valued function, so we can talk about the differentiability of this function using our standard notion of differentiability. So f is c to the k means all right, we have a map between two manifolds. That map is said to be k times differentiable, ck, continuous kth derivative. And what does that mean when f is a map between manifolds and not between Euclidean spaces? Well, it means around every point, oops, I didn't say that. Around all points P and M, you can find a chart and a coordinate presentation of our map such that all these components here are k times differentiable with respect to x mu, where x mu is the coordinates of your chart. So it's a bit of a handful, but it captures exactly the notion of differentiability that you will, it upgrades the notion of differentiability that you know from vector value calculus to this sort of curvy version of vector value calculus. And those are the maps we're going to allow in this course. Of course, I've said we're going to set k as infinity almost always. In the case where k is infinity, don't need scare quotes, we'll just say when k is infinity, we have a different word for it. We say that f is smooth. Now, there's a subtlety here which you get used to seeing. You may not have noticed it at this point, but you will get used to asking this question. There's a certain set of questions that in science that you always have to ask. And the question is here, is this independent of the charts we chose? Is this definition independent of the charts we chose? Because if it depends on the charts you chose, it's not a very good definition. It's not even, we say it's not well defined, right? And you have to convince yourself that if something is k times differentiable in one chart, and you just, on Monday you use that chart and on Tuesday you use a different one, that those two notions coincide. It doesn't matter which representation you use. And I'm not going to do that. That's a nice little exercise for you. One of those standard questions that you have to ask whenever you define something. That's it. So we've got our category now. We've actually can start doing math. We want to do physics, but we can at least do math. Our objects are manifolds, CK manifolds, and our morphisms are CK maps between these manifolds. And K will usually be infinity. Now, there's a really special kind of map that will concern us. This map is the one that says two things are equal. So you want to be able to determine when two things ought to be like the same thing. That's very important. When you've got two objects, two manifolds, and you want to compare them, and you want to say, okay, this one's the same as this one. You've got to say, what is the notion of sameness that we're going to use? Sameness might mean that they have the same dimension. Maybe that's enough for two to be the same. Like that's certainly true for Euclidean spaces, right? If I have r to the m and r to the m, then they're the same, right? The dimension is the invariant here that says that two things are equal. What's sameness for manifolds? Well, we have to give a definition for that. So that F be a map between two manifolds. Well, not any map, we're going to quite a special one. It's at least got to be continuous with a continuous inverse. That's what homeomorphism means. But it's going to be even more special than that. So we've got a map, we've got two charts around our points, blah, blah, blah. Now, if it turns out that this coordinate presentation here is invertible, so i.e. there exists a function with coordinate presentation given by F inverse. Well, that's guaranteed from the definition of homeomorphism. There is an inverse for sure. But, and here's where we add some extra conditions, both this coordinate presentation and the other one are differentiable, k times differentiable. K times differentiable. Then F has a special name. It's called a diffeomorphism. CK diffeomorphism. Diffeomorphisms are really special. They're nice smooth functions, and their inverses are smooth functions when k is infinity. And that sets up a notion of equivalence between two manifolds. Two manifolds are equivalent. We consider them to be the same manifold if they're diffeomorphic, or if there exists some nice smooth map between them. So in that sense, like the sphere is really just the same manifold as the slightly deformed sphere, because there really is a nice differentiable map between the sphere and the slightly ellipsoid sphere. That's the notion of equivalence we're going to have in this course, most likely for a great part of the course. You don't have to define that as your notion of equivalence. That's the thing about maths, right? What you deem to be equivalent is up to you. And you might say that two manifolds are equivalent if they're only homeomorphic, if there's some continuous map between them. Or, I don't know, you might be more strenuous and say that the manifolds are equivalent if this diffeomorphisms have compact support. Or there's many, many ways to refine or coarse grain your notion of what the word same means. Certainly in general relativity, the notion of sameness is captured by diffeomorphism. So this sounds all very abstract, right? Objects, morphisms, blah, blah, blah. But actually, I claim that this is much closer to physics than it looks. So in physics, you have to answer questions as a physicist. When are two things the same? When do you deem them to be the same thing? And you can come up with various notions, and that really determines how physical theories look. So you could say that two things are the same if they're physically indistinguishable. I see people nodding. That seems like a reasonable notion of sameness. If I have that thing here and that thing there, and I cannot tell the difference between these two things, then are they not the same thing? So that actually defines a notion of indistinguishability, and that depends on the observations you're allowed to make. So this cup of water, that cup of water, they look the same if I use my eyes. But if you had an electron microscope or whatever, scanning, tunneling electron microscope, you could look further and see that they're not the same cups of water at all. The microstates are completely different inside these cups of water. So the notion of sameness is a physical question. You have to determine what you think same means in physics. And that, in turn, tells you what kind of maps you're going to say tell us when things are equal or not. So this looks abstract, but actually it has operational motivations in physics. What can you measure? What is indistinguishable? What's the same? And you can get some really interesting physics coming out of by changing your notion of what same means. Now it's sort of worth noting who left their phone on loud? It's worth noting that the composition of two diffeomorphisms is a diffeomorphism. You have one, you have another, do one after the other, that's also a diffeomorphism. And that's that leads to a trivial looking observation, but one that's sort of surprisingly rich and occupies all of us in various parts of research to this day. So here it is. That means that the set of some of diffeomorphisms from some manifold M back to itself forms a group. And boy, what a group it is. This is a very, very interesting group indeed for very many different kinds of manifolds. And I'm going to dwell a little bit on the simplest, arguably the simplest example. I can't resist this digression. Let's take the simplest example of a manifold. So the simplest example of a manifold might be R1, right? You might think that the real line is a very, very simple example. I mean, in some sense, you're right. But actually, that turns out to be even more complicated than the circle. The circle is really, in a lot of senses, the simplest one-dimensional manifold there is, because it's compact and the real line isn't. So this is sort of why the circle is a little bit nicer. And it doesn't have any boundaries. So we haven't talked about manifolds with boundaries. I mean, you can, but I guess to talk about all the interesting theory in this course, we just don't need manifolds with boundaries. But everything can be extended to that case if you want to go through the work. So here it is, the simplest example, right? How hard can the circle be? It's a circle, you could draw it. Well, it's not very hard, right? As a manifold, it really is pretty simple. It's just a circle. But, boy oh boy, is that group interesting. This is an astonishingly interesting group. So I'm going to tell you a little bit about this group. I spend a lot of time with this group. I like it a lot. A lot of people do in physics and in math because it comes under another name. Yeah, a question?
Is it the set of diffeomorphisms from M to M or N?
Oh, the question was, is this the set of diffeomorphisms from M to M or M to N? It's M to M. So it's got to be the same manifold. Otherwise, we give it a different name. If it was from M to N, then we would put a comma N in here. But you can do that, but this is already sufficiently interesting that we'll stop there. Yeah. So this group it appears in all kinds of places. Now I'll give you the place where it appears most strongly in physics. It has a name. It's called the chiral half of the conformal group. So it appears in conformal field theory, if you've heard of that thing. It appears in a vast number of other places. In maths, they're called circle groups. And there's just so many interesting questions about these groups. Now, the beauty of these groups is that you could have defined them already, I guess, at your early undergraduate, sort of late high school stage, because you can draw them. You can draw elements of this group super easy, right? So how do you draw a diffeomorphism from the circle to the circle? Well, here's how you do it. You identify the point 1 on the real line with 0 on the real line. So whenever you reach the point 1, then you sort of loop back to 0. And then you just draw functions. So a diffeomorphism from the circle to the circle is nothing other than something you can draw. It's a monotonic increasing or decreasing function that's different, sort of smooth nice and smooth. And when you get to 1, it better be the same as 1. So it loops around. So at this point here, the function goes all the way up. And then at that point here, it's equivalent to that point there. So that gives us a map from the circle to the circle. And it better be that the derivative of the function everywhere is k times differentiable. And at this point here, the k derivatives of the function better match the k derivatives of the function down there. So elements of this group look like that. They're just smooth functions you can draw without lifting your pen, and you just make sure that they sort of patch up nicely at 0. Also, they can look a bit different, right? It can be that your function sort of starts up here, goes there, that's the same as here, and then it's got to have the same derivative there. It can also look like this. So this group consists of all functions that you can draw on the paper that are k times differentiable and that map 1 to 0, and that behave nicely when you identify 1 with 0. And under composition, right, you do one function then the next. Every such function has an inverse, blah, blah, blah. We often talk about diff plus k. So that's where it's monotonic increasing always, because it could be monotonic decreasing. That's also an allowed diffeomorphism, but that's a disconnected part of the groups. Super fascinating group. And that's exactly, they are directly related to things called conformal transformations in quantum field theory. So that's one physical place where they immediately turn up. They're also related to fluid dynamics, these groups, vast number of places. And you can ask surprisingly easy questions that are, to this day, sort of really, really difficult and completely unsolved. So just, how does diff k of S1, how does it live in diff k minus 1 of S1? So obviously every infinitely differentiable function is a k times differentiable function, so that's a subgroup, there's a subset of those functions that live, and we have that inclusion there. And exactly how much bigger is this set than this set? Difficult questions. We don't know the answer. Another fascinating topic that I'd love to talk about, and we may in some sense get to talk about this in this course, is the representations of this group. What are the unitary representations of this circle group? If you can answer that, you're doing conformal field theory. We will, I hope, meet this towards the end of the course again. So it's a deeply fascinating group, and this is the simplest one. That's just S1. Now, there's a bigger one. If you have as your manifold a Lorentzian manifold, Minkowski space, and you have diff plus, or just diff of that, then that's the gauge group that determines relativity, general relativity. So this already at this very simple stage in the course, we're able to define fantastically deep, complicated, subtle objects. Also turns up in string theory. All right, we're going to have to drag myself away from this group. And we're going to talk about some special maps in the category of manifolds. Okay, some special maps, some special classes of maps. There's two particular classes that will occupy us a lot in our theory, and those are curves and functions, what you'd call the analog of a curve and the analog of a function. So let's start with curves. What's a curve in a manifold? That's a function from a one-dimensional manifold to a whatever, an m-dimensional manifold. That's what a curve is in real space, right? A curve is just a one-dimensional curve. Well, it's a map. At least it's a map. And it's going from the open interval with endpoints A and B into your favorite manifold, M. So that's my notation for open intervals. That's the correct notation for open intervals. I hate this notation. This is bad. Don't like it. Now, let's draw a picture to get a sense of what it looks like, what the things are. So it's an open interval, so it doesn't include its endpoints, and a map C is a map from this to our manifold M, and that means to every point here we have a corresponding point over here in our manifold, and we want to talk about its coordinate presentation. We always need to choose coordinates if we want to answer questions like differentiability, blah blah blah. So we choose a chart, that's U here. And in this chart, the curve looks like that. And you can follow these maps around and convince yourself that there must be a map that goes from this open interval AB directly to R to the M. And what's that map? Well, you first do C, then you do phi. So first do C, then phi. All right, that's a curve. We've defined a curve. There's one other special class of map that we want to focus on a lot in this course, and that will be functions, what we call functions. So a function is a smooth map from M to the R, to the real numbers. It just gives you a real number per every point on the manifold. So here, the appropriate picture is a little different. Here's R. We know how to draw that manifold. It goes off to ever. And a function from M to R is some map from our manifold to R. So again, some point P gets mapped to some F of P. And we take some chart to understand this. And if you follow this around, you see that there must be some map that goes from R to the M directly to R, and that one is a little different. We first have to do phi inverse and then F in order to get from Rm to R. And the collection of all functions on a manifold, we give it a name. It's called curly FM, which looks exactly like the symbol we used for differentiable structure yesterday. Since we're not going to talk about differentiable structures again in this course, I'm going to overload that notation and just use the same symbol. So whenever you see curly F like that now, that means the set of all functions on the manifold M. All right, so that's it for our category. Our category, the set of things that we're going to talk about are K or M dimensional manifolds. The set of maps between them are going to be smooth maps. That's our category we're going to talk about from now on. Let's start doing some actual calculus though. So to do that, we're going to need to understand the notion of a derivative. That already will occupy us for a little bit. Also, we want to do many variable calculus. We know how to do many variable calculus. That's pretty easy. You learned that in undergraduate. Now we want to do many variable calculus on our more general category of differentiable manifolds. And to do that, we need to talk about vectors, right? So vector calculus is how you do calculus in many dimensions. So we need to talk about vectors on manifolds. And so our next big topic that we have to get through and really this is when physics starts to appear in our course, is that of tangent vectors. So we want to talk about changes between points. Physics, the equations of motion of physics are usually local in time and in space, usually. And that means that they take the form of telling you the change in something and the direction that something changes. So if you have a point, a pendulum for example, the change in its coordinate is given by a vector, which tells you where it's going to go to. And that Newton's equations will tell you how to calculate that vector. Similarly, all the other equations of physics, they almost all have that kind of form. Something changes, and the rule for how it changes is given by usually a vector. Sometimes these things happen in infinite dimensional spaces, but usually that's the idea. It's not impossible that in physics things could change non-locally but it's very hard to reason about that. And we've managed to successfully describe most of physics without needing to do this, so why bother, right? So let's start with, but to do this on manifolds, we need to say what is a tangent vector. So the way to do that, there's actually sort of 3 definitions that I'm aware of for how to define tangent vectors. I'll show you 2 today, and I'll try and remember the 3rd. And they all are aimed at generalizing the notion of vector in real space. So this is, when you define something in maths or physics even, and you define it by analogy with another thing, then you have to work out what aspect of that thing carries over to the new setting. And you might find that the original thing that you're trying to generalize, namely a vector, there might be different aspects to what makes a vector a vector. You know, why is this quantity a vector? And you take those features or those properties of this thing that you call a vector, and then you ask that they carry over to a new setting of manifolds. And then you might see that there's different ways to take that definition across the manifolds. And then you have a real problem, because you have multiple likely definitions for the right thing. And it could be that they end up with different results. Luckily, in the case of manifolds, sort of every conceivable way you have of capturing the vectoriness of a vector seem to carry over to something that's equivalent notion in the case of manifolds. So I'm going to show you the first vectoriness condition. And the way to do that is to take a setting where we understand things much better, namely embedded manifolds, and to work from there. So let's take this very concrete class of manifolds that basically we're always going to work with anyway, and that is embedded manifolds. And ask, what is a vector in that case? What does it mean, a vector on the manifold or in the manifold? So you have there's a kind of pretty clear notion that if you draw, you have some Rm, and you have some embedded manifold, and in Rm that's just on the board, that's just a line, but you could imagine that as like some surface. It's sort of pretty clear what a vector in the manifold must mean. It must mean that you go to a point and that the vector is exactly parallel to this manifold exactly at that point, and maybe infinitesimally far away it isn't, but it just that point here, sorry, infinitesimally far away, it's still parallel to this manifold, and not infinitesimally, it might be different. So a vector is somehow something that's tangent to this manifold everywhere. And we can talk about the words tangent to at a point when you have an embedded manifold. Easy, right? You just sort of drag a vector around, plonk it on the manifold, its base point on the manifold, and if it doesn't point parallel to it, then it's not tangent to it. So look, that's not tangent, right? Easy. So this question can be answered within vector calculus. And so we're going to see what features we have of this answer. And the feature of a tangent vector in the case of an embedded manifold is that a tangent vector is always normal to the normal, right? It's orthogonal to the normal vector of a manifold. That's what it means, tangent vector, in many variables. So the set of all tangent vectors must be the space orthogonal to the normal vector, and we know how to calculate the normal vector. We're going to give it a name. The space of all tangent vectors to a point x in M is just going to be the complement of this set of vectors here. I'll do an example in a second. Vector space even, that's an interesting observation right there. Two vectors are tangent if you can add them and they're still tangent. You can multiply them by a scalar, they're still tangent vectors. Where Fj define M. They're the defining functions for M. So that's one notion of what it means to be a vector on a manifold. We say a vector is a tangent vector if it's complement to all the normal vectors. And we'll just do an example just to get like some sense of how it looks. So the simplest embedded manifold that I could think of, well, I'm not going to take the simplest, I'm going to take the sort of next most simplest example. The simplest one that I thought of is the curve y equals x squared in R2. So the curve y equals x squared is an embedded manifold. And I'll first prove that statement. So that's M here. And it's an embedded manifold because this following function here vanishes on M. So it's defined by the vanishing of a function, so it's an embedded manifold. And that function has this property that you need for it to be an embedded manifold, namely that all its derivatives are linearly independent. That's okay because it's one-dimensional. So then we say that the tangent space to the manifold at point x is the complement of the gradient of this function. And so the gradient of this function, grad f, well, let's work it out. It's df dx, df dy at the point x, y. And what is that? That's minus 2x, 1. So the set of tangent vectors to this curve at the point, so x here, that's a bit overloaded, I'm sorry about that. That means the pair x, y, right? So the set of tangent vectors tangent to this curve, I mean, you know how to work it out, right? You work out the derivative, you find that that gives you the gradient of the line that kisses the curve there, and then you move it up till it actually touches the curve. And then you're good to go. That's what a tangent vector is to that curve. And let's just see that this line here, that vectors on this one-dimensional vector space really do come from this alternative definition. And, well, if you work out what vectors are orthogonal to that vector there, then you come up, I hope, fairly quickly with the idea that that probably should be these vectors. The span of vectors of the form 1 and 2 times x. And, you know, rise over run looks good. It's actually exactly the tangent vectors to this manifold. So that's one idea of how to define tangent vectors to a manifold. If the manifold just happens to be embedded, then you're already good to go. Just use this formula here. And actually, I just don't know a manifold where I don't know it as an embedded manifold. So in some sense, this is already it. We could sort of stop here and use that as our definition. I mean, of course you can construct manifolds that aren't obviously embedded, but that's not the important point here. The point is that, is it obviously, are those ones of any use in physics. And the ones that are of use in physics tend to be obviously embedded in RM somehow. Tend to be, not always. But, and you might be satisfied as a physicist with that notion. But as a mathematician, you would have, if you put on your mathematician hat, you would have grounds to be a little concerned by this definition. Because this definition seems to depend on your embedding. So it's a bit arbitrary, isn't it? Like, what if you had the manifold embedded in two different ways, in two different manifolds? Which one's the right one? So you'd have to go down the road of proving the definition is independent of the embedding. Of course, no problems there, but you have to do that. But then you might be still concerned, what if there are manifolds that can't be embedded in RM? Then what's the right way to talk about tangent vectors? So this was even an open question for a while. Do there exist manifolds that can't be embedded in RM? Or at least if they're so-called orientable, they can be. You can always embed them. Although somehow this ends up not being a very interesting thing to do. Instead, you just say, I want to come up with an intrinsic definition that works for all manifolds, so I don't have to worry about looking for that embedding. And that's an intrinsic definition. That's the next one I'm going to write down. So this notion here, just to emphasize, captures the vectoriness of a tangent vector by saying that it's orthogonal to the normal vector of the surface. The next definition captures the vectoriness of a tangent vector in a completely different way. It says that a tangent vector is really like the velocity vector of a curve within the manifold. That's also a tangent vector. If you tear around a racetrack, your velocity vector will always be tangent to the racetrack in your car. This is the next definition of what a tangent vector could be. We're going to define them as velocity vectors to curves lying in M. So I'm going to take a slightly more complicated example, namely a sphere, surface of a sphere. So again, the sphere is embedded in R3, so we know what it means tangent, according to our first notion. But we want to capture the notion of tangency in a different way. So we imagine that you have some curve. You could draw an arbitrarily complicated curve as long as it satisfies the definition of a curve. You have a curve in the sphere, and you know what that is from our previous discussion, some map from the real line to the sphere. And we can talk about the derivative of this curve, right? Because it's a smooth map. We take some chart to the real R2, and it looks something like this. That's the curve. In this case, it's sort of two pieces of the curve that land in that chart. And then you take velocity vectors of this function that goes from C, phi, first C, then phi. So you then take velocity vectors of this curve here. And those will define, vectors in R2. And then you say that this idea of something being a velocity vector, that's really what a tangent vector is. So let's try and capture that as a definition. And to do that, we're going to have to work a little bit harder. We're going to do it by using another trick, another general kind of trick. And that trick's motivated by this velocity vector construction. So the idea is we're not going to directly define a velocity vector to be a tangent vector. It still depends on embeddings and so on. Instead, we're going to observe that two curves that touch at the same point and have the same first derivatives define tangent vectors, or have the tangent vectors which are scalar multiples of each other. You know, you're just either going faster or slower, but you're still going in the same direction. And so a tangent vector is really this, it's something that you get, it's defined by really not just one curve, but by an equivalence class of curves. It's that thing that's common to all curves with the same velocity vector and same point x. So in our second definition, we're going to set up our tangent vectors to be equivalence classes of curves. Two curves are now said to be equivalent if, when you work out what their image is at the real number 0, that it's the same thing, it's the same point in M. We'll give that point a name, call it x. And 2, the derivatives are the same at that point in the corresponding coordinate chart. So that captures this notion here. You can check that that defines an equivalence relation on curves. One curve is equivalent to another, and then this curve is equivalent to a third one. It implies that C1 is equivalent to C3. It's transitive, reflexive, blah, blah, blah. You can check all these things.
But we define the open interval of A to B as that the 0 has to be in.
Yeah, for this definition, 0 has to be in. The question was, didn't we just define curves with respect to open intervals? Is 0 in there? Well, by assumption, 0 is in there. Otherwise, this wouldn't make sense as a definition. Good question, right? So 0 is defined to be in there. So this is an equivalence class on curves containing the origin. And a tangent vector is that thing that's common to all of these curves. So this is when you turn the property into a definition. Very cunning trick. If you don't know how to define something, find a property common to a bunch of things you know about, and then define that something to be that equivalence class. So a tangent vector x on our manifold M is identified with an equivalence class of curves under this equivalence relation here. So this is my notation for equivalence relation, equivalence class, sorry. And that's just defined to be the set of all curves C twiddle of t such that C twiddle of naught equals C of naught, and of course the derivatives of their coordinate presentations are equal as well. I could change the to an, then that's a bit better. So what you're meant to think of here is like think of the set of all curves that contain the origin. So that's not the manifold M or anything. This is just my visual representation for the set of all curves. So each point in this set is an infinite number of points, and each point is some curve containing the origin. All these points. And a tangent vector is a whole bunch of curves which are all equivalent according to this notion of equivalence. So that divides this set up into big pieces, equivalence classes, and tangent vectors are now, in this case, defined to be these equivalence classes. That's certainly an intrinsic definition. We never really needed the embedding of the manifold M inside Rm to do this. There's another definition. Will we get to that today? I guess so. There's even a fourth definition that occurs to me. Now we're not quite done, to be clear. With this second definition of what a tangent vector is, you have to argue that this is even a finite dimensional vector space. It's not even clear, right? You have some mega infinite set and you find some equivalence classes on that set, and then you mod out by those equivalence classes. That's what that means here. Is the resulting set even like a vector space? Is it finite dimensional? What properties does it have? I'm not going to prove those to you, but I just claim or leave it as an exercise that indeed that is the case, and that it matches the previous definition when the manifold's embedded. So that's up to you to check. I mean, it's not the world's most difficult argument, but you sort of have to think it through. Instead, I want to emphasize that, you know, what makes a tangent vector? A tangent vector there's many aspects to vectoriness. Let's capture another aspect and try and generalize that. I'm going to do this enough times that we have access to different ways of working with tangent vectors, and that you see that these notions are all equivalent, or at least you can sense that they're equivalent, and therefore it's that tangent vectors as a notion sort of makes some more than superficial sense on manifolds. So this next definition exploits the idea of tangent vectors as being like derivatives of functions. This is not like the most obvious way of generalizing a vector idea, but a little bit of thought, I hope, and then you'll agree. So here we have a curve. We still have a curve in our manifold, but now we're defining a tangent vector to be the result of doing a directional derivative. So that's something you can do from vector calculus. And that makes intrinsic sense as well, right? So the directional derivative of a function along a curve is pretty easy. You just evaluate the function on the curve, you differentiate it with respect to this curve parameter t, and you evaluate that at t is naught, and that's the directional derivative. Yeah?
Do the function s have to be defined globally?
Does the function f need to be defined globally? No, only locally, right, for this definition to make sense. So if you didn't know about manifolds and you just saw this expression written down and you just m was r to the m, that would make complete sense, right, what I just wrote from vector calculus. Directional derivative of a function along a curve, something you've seen before, I hope. Guess it's the right time to draw a picture. Well, it's always a good time to draw a picture in differential geometry. So we have a manifold M, we have a function f, we have the real line here. So far so good. We have a point, which in this case is c of naught. So we should draw a chart around that point. And that point is the image of a curve, C. Is this the picture I want to draw? And there's also in the background a chart here as well. So it's worth pointing out that in terms of local coordinates, the directional derivative of f, you can work it out just by using chain rule. And this is the mind-bending part about this definition, if there is a bit. You can get the same answer here by applying an operator to f. So the set of tangent vectors according to this definition is the set of all differential operators of this form. So we make the definition, this is just motivation, that the set of vectors tangent to the point x is the linear space span, the linear space of operators of the form of first order derivatives operators, where these x mu's are just numbers. And what numbers are they? Well, they're just a list of numbers from Rm. Another definition of a tangent vector. Yeah, question?
The definition, first formula line, wouldn't it be dx by d mu, dx mu by dt of t? Because we define x mu to be a function on AB, I guess.
Yes, x mu is a so in this line are we talking about?
Yes, maybe the notation is not so clear, but before, like on the left side of the equal sign, we have this expression where it kind of means f after c derivative.
That's right, yeah.
And this is like not x mu after c derivative, like comparing the notations. This is really x mu derivative.
Sorry, yeah. You mean this, right?
Yes.
Yeah, sorry. Yeah, that's right. Yeah, there's an additional c of t that shouldn't have been in there, according to the notation. And then I think I repeated it down here. No. Okay. There's yet another definition of tangent vectors that we could use in this course. I won't cover it, but I will mention it just in case that you are interested in algebraic geometry. This would be the one that you would use. So you set up the set of functions that vanish at the point x. In the manifold. And then this is an ideal. Then you square this ideal. And you take the quotient. That's also another definition of the tangent space to a manifold. That's really, I'm doing that from memory, so that needs to be checked. But that's only if you're interested in algebraic geometry. Would you want to see the connection to tangent spaces like in that particular way? All right. I guess we'll stop here. So next lecture, we're going to do a teeny bit of physics. We're going to talk about Lagrangian mechanics, because we actually have assembled enough data to be able to do that. So we can talk about Lagrangians now. So if you think right back to mechanics and how you define Lagrangians, the Lagrangian function is a function of position and velocity. But to talk about velocity, you need tangent vectors. Well, we have those now, and we have position, so we can talk about Lagrangians. And we can even express the extremal principle and the action. We can set up all that stuff. So we can do mechanics on manifolds, and we'll do that briefly in the next lecture before moving on to Hamilton mechanics in this formalism. But for now, I think we'll stop there. Thank you very much.